Hello again, how are you doing? Let's continue with Euler and Lagrange. Let me solve a more elaborate example before getting into the stationary action. Let's consider now that a spring is hanging from the ceiling of our laboratory. So here gravity will play its role. And let's assume that the spring is wrapped around a thin massless rod so that it moves along that straight line on the vertical plane. I'll call lowercase l to the equilibrium length of the spring and x to the displacement with respect to that length. Let's write the Lagrangian now. Because of the kind of motion, I'm going to use polar coordinates. The kinetic energy is 1/2 of m times x dot square plus l plus x square theta dot square. The first term is the radial component and the second is the tangential one. The potential energy for this has two components, the gravitational one and the elastic one. If I consider the ceiling to be the origin of the gravitational potential, then I need to calculate the vertical distance of the mass to that ceiling. So negative mg L plus x times the cosine of theta plus the elastic term 1/2 of kx squared. The Lagrangian is then look that this Lagrangian has two variables, x and theta. Well, this is a two-dimensional problem, so it makes sense. Now, the equations of Euler-Lagrange apply to both variables x and theta. Look that these variables have different units, but I don't care. Let's apply the equations to x and x dot. And let's now apply it to theta and theta dot. So we have these two different differential equations for the system. Well, the first one is F equal ma. For the radial component, we have the gravity force, the force of the spring, and the centripetal force. Remember that in polar coordinates we are not in an inertial frame. And the second equation is the tangential F equal ma, where the second term is Coriolis force, again, due to not being in an inertial frame. So these are again Newton's second laws. Well, you could argue that why do we need to go this far if we already have Newton's laws? I'll tell you that the energy is a scalar and force is a vector. Sometimes writing F equal ma through a three-dimensional vector is not an easy task. And usually finding the energy of the system, it usually is an easier task. And do not worry, we will be able to tell the forces at the end of the Euler-Lagrange process. May the science be with you.